6.2 day 3 focuses on normal distribution. The first part here says, suppose x is normally distributed, the mean of x is 50, the standard deviation of x is 8, and y is normally distributed. It's a different random variable. It says the mean of y is 30, and the standard deviation of y is 6. So if we were to add together these two random variables, it would be x plus y. What would the distribution of x plus y be like? And when we're supposed to describe distributions, we can use the SOX acronym. So let's talk about shape, center, and spread. Well, first of all, as far as the shape is concerned, if x was normally distributed and y was also normally distributed, then when we add them together, x plus y will also be normally distributed. And we know that because x and y were both normally distributed themselves. Okay, so how about the mean of this distribution? The mean of this new x plus y distribution is actually pretty straightforward. It's what you might guess. We would take the mean of x plus the mean of y, which we're given those. The mean of x is 50, and the mean of y is 30. So the mean for this new distribution would just be 80. And then as far as the standard deviation goes, well, as long as these two variables are independent, we just need to take their standard deviations, and it's like the Pythagorean theorem, right? Standard deviation of x, square it, plus the standard deviation of y, square that, and then we take the square root of that. So we have 8 squared plus 6 squared, so the square root of 100 is 10. So that describes the shape, center, and spread. So we need that to answer the next question. It says, what's the probability that x plus y is going to be greater than 95? Thankfully, we're really good at answering these normal distribution questions by now. So we know that the distribution is normal. So let's start with that. We know it's normal. We draw a normal curve, and we know the mean, and we know the standard deviation. So we can label this curve. So this curve represents our x plus y distribution. We know the mean's 80. The standard deviation is 10. We just need to mark off where we think 95 would be. So what's the probability that this x plus y is greater than 95? We mark off 95 and we shade everything above it. We want to know about the stuff greater than 95. So we can use the normal CDF command in our calculator. So we can say using technology, the command normal CDF. The lower bound, we marked it off at 95. The upper bound here would be 1E99. And then let's give the mean as 80. The standard deviation is 10, which gives us our answer of 0.0668. So what does this area represent? Well, that answers the question for us. What's the probability that we have x plus y greater than 95? That probability is 0.0668. So that answers the question. The next part here looks at what if we did x minus y? What would the distribution for x minus y be? Well, since x and y are both normal, x minus y will still be a normally distributed random variable. So whether we add or subtract these random variables, as long as they started out normal, when we combine them, the distribution will still be normal. And as far as the center goes, where's the mean going to be at? Well, it's exactly what you'd think. We'd take the mean of x minus the mean of y, so 50 minus 30. Our new mean for this random variable, x minus y, would be 20. So we've got the shape, check. We've got the center, the mean here, check. Next is the spread, and with normal distributions, again, that's standard deviation. Just don't forget that when we're talking about the standard deviation, we're still combining two things. So when we're combining two random variables, that still creates more variability. So the standard deviation is always a sum. Just like the Pythagorean theorem, this is always a sum. So we add the two variances here, the two sigma squareds, and then we square root it. So it's really going to be the same as we got in the previous result, square root of 64 plus 36, which is 10. Okay, so really nothing new so far. You know the shape stays the same, right? Stuff stays normal. You know how to get the mean, and you even know that standard deviation, you still add it, even if you're subtracting two random variables. This type of question, though, is the one that's new and the one that's really important for these notes. So you'll see a question that says, what's the probability that something is bigger than something else? In this case, what's the probability that x is bigger than y? And if we go back, you might think there's a pretty good chance that the x would be bigger than y. I mean, x has a higher mean, right? So there's a pretty good chance that x might be bigger than y if you just pick a random x or if you just pick a random y. We're actually going to use this x minus y distribution to answer this question, though. This is still a normal probability calculation. So the probability that x is greater than y, I just want you to look at this in a different light. What if we subtracted y on both sides here? So subtract y, and you should recognize something from above. So the probability that x is bigger than y, that's really just a fancy way to say, what's the probability x minus y is greater than 0? And we get that by subtracting y on both sides here. So hopefully that made sense to you. That's kind of the big takeaway from these notes, because we already know what this distribution looks like. X minus y, we know the mean is 20, we know the standard deviation is 10, so now it's just a normal probability calculation. Let's mark off 0 somewhere down here, and we want to know what's the probability that this random variable is bigger than 0. So I know we've got 0 marked off, we'll just shade everything above 0 here. And we could go right to the normal CDF calculation. The lower bound would be 0, the upper bound would be 1E99, or if you're old school, we could just get the z-score for 0 and look it up on the chart. So this is for those people that prefer to use the chart. The z-score for 0, we would take 0, subtract the mean, and divide by the standard deviation, which gives us -2. So what's the probability that we get a z-score of -2 or bigger? A p area to the west or below a boundary, to the left of it, I should say. So I could tell you how much area is below the boundary here, but I can't rightfully tell you how much area is above it. But we know that the curve is perfectly symmetric, so it should mean that the area above the -2 z-score would be the same as the area below the +2 z-score. So if we look up 2 on our z-score chart, that gives us 0.977. And you can check that using the normal CDF command here. So the probability, in this case, that we get an x minus y greater than 0 would be 0.977. And the big takeaway is when you see a question like this, a random variable compared to another random variable, can you subtract and get 0 on one side? In this case, we already knew all about this x minus y distribution. That kind of set us up for this problem. Okay, so example 1 says, Mr. Bishop likes between 8.5 and 9 grams of sugar in his coffee. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with mean 2.17 grams and standard deviation 0.08 grams. If Mr. Bishop selects 4 packets at random, what's the probability his coffee will taste right? And I do definitely enjoy coffee, by the way, if you know me. So let's start out with defining our random variable here. And we'll just use x. I guess we could use c for coffee, but x is going to be a randomly selected sugar packet. So just like in the state step, we're going to start off with defining the variable. So the random variable we're going to use is called x, and it's just going to be one single randomly selected sugar packet. So x we know is approximately normally distributed. The mean is 2.17 grams. The standard deviation is 0.08 grams. And then so for the coffee, let's call that y. So we have 4 packets, right? 4 randomly selected sugar packets, and we get this new random variable, we'll call it y. So we know y is normally distributed, and it's got 1, 2, 3, 4 packets of sugar in it. So x1, x2, x3, x4. That's the first packet, second packet, so on. So that's what y represents. Y is our 4 sugar packets, the first one, the second one, the third one, the fourth one. And we know y is normally distributed because each one of those x's comes from a normal distribution. And then we need to know what's the mean and standard deviation of y. So y is like the coffee I get with these 4 packs of sugar in it. So what's the mean of y? Well, you just do the mean of each x, which we actually know the mean for each one of those x's is 2.17. So 4 times 2.17 is 8.68 grams. That's the mean for y. So we just add up the mean for the x's 4 times. And for the standard deviation for y, it's not quite as easy as just adding up the standard deviations for each x. We want to do sigma squared for each one, add all of those up, and then take the square root. So that's really 4 times this standard deviation squared. So 4 times sigma squared. And we can take the square root of each one of these, right? So the square root of 4, that's easy. That's just 2. And then the square root of sigma squared is just sigma. So we have 2 times the standard deviation of x, which is 0.16 grams. So the question, what is the probability his coffee will taste right? That's actually a normal probability question, something we could use normal CDF with. Well, now we know the distribution, y, it's normal, there's the mean, there's the standard deviation, and that comes from the 4 packs of sugar. So the question being, what's the probability that the coffee tastes right? In this case, to taste right, apparently it's got to be between 8.5 and 9 grams of sugar. That's what it starts out by saying. So y, from the 4 packs, we have to get between 8.5 and 9 grams of sugar. Okay, so if this is a normal probability question, we can start by sketching a normal curve, and this is going to be our y distribution. The mean's 8.68, we'll label it. The standard deviation is 0.16. And then let's mark off about where we think 8.5 and 9 would be. And let's shade everything in between there. And so our answer really is, what's this area? And we can use normal CDF to figure it out. Or again, if you're old school and you like z-scores, you can do that too. Seems like the calculator is way quicker in this case, though. The lower bound would be 8.5. The upper bound would be 9. Then we give it our mean and our standard deviation. And our answer is 0.847, which based on how much of the curve we shaded, that seems pretty reasonable. So in context, what does it mean that we got an area of 0.847? Well, apparently, that's the probability that Mr. Bishop's coffee actually tastes right. So we can say there's about an 84.7% chance that Mr. Bishop's coffee will taste right. By the way, I'd usually drink coffee just straight black, but makes for a good example in this case. All right, example 2 talks about speed dating. It says, suppose that the height m of male speed daters follows a normal distribution with a mean of 68.5 inches and a standard deviation of 4 inches. The height f of female speed daters follows a normal distribution with a mean of 64 inches and a standard deviation of 3 inches. What is the probability that a randomly selected male speed dater is taller than the randomly selected female speed dater he's paired with? This is going to be a big deal for some guys because they think they need to be taller than their date, right? So let's start out with the random variable. So let the random variable, we'll call it D in this case, right? D, which is m minus f, hopefully that makes sense. Our random variable D is going to represent the difference between the male's height, which is m, and the female's height, which is f. So right away we know D, the difference, follows the normal distribution since m and f are both normally distributed. We need to know the mean now and the standard deviation for the differences. And if you're wondering why I didn't do f minus m, well, it's actually going to be easier in this case to do male minus female. Let's take a look at the mean, for example. So the mean for D, the difference, would just be the mean of the males minus the mean of the females. So 68.5 minus 64 is 4.5 inches. We could go the other way, but then we'd have a negative answer. Also, just wait until we get to the probability calculation to find what we're looking for. The standard deviation, you won't be fooled in this case. You know that when we're combining two random variables, we're actually creating more variability, so we still need to take the standard deviations from the males and the females, square them, add them up, and take the square root, just like the Pythagorean theorem. So in this case, that's 4 squared plus 3 squared, which gives us the square root of 25, which is 5 inches for our standard deviation. Okay, so we got this random variable d. It's normally distributed. We know the mean, and we know the standard deviation. So that's going to help us answer this normal calculation. Think about the actual question for a moment. It says, what's the probability that a randomly selected male speed dater is taller than the randomly selected female dater he is paired with? So as far as the probability notation goes, that's the probability that the male is taller than the female. So that's the actual question. What's the probability that the male is taller than the female? And just like I said at the beginning of these notes, you're going to run into these questions. Can you handle them? Do you know how to handle them? Is what we're after. And think about this. We just did all this work to compare males and females, right? Our random variable d was the difference, and it was male minus female. So if you could just make this look like this, we'd be in business. So when you run into this is actually pretty simple if you see it. You just subtract f on both sides. This is the same thing as asking, if I subtract f on both sides, I'll have 0 over here and m minus f on the left-hand side. This is the same thing as asking, what's the probability that this thing is greater than 0? Or when I say this thing, we just call that d. So in other words, what's the probability that our difference is greater than 0? And we know all about this random variable d. We know the mean, we know the standard deviation, and we know it's normally distributed. So we can just draw a curve and label it. We know the mean, 4.5. We'll actually just mark off 0 somewhere down here. And then we're going to shade everything above it. So if you just think for a moment, it should be over 50% of the time that the male is taller than the female here, just given the average height of a male compared to the average height of a female. Right? So it should be over 50% of the curve that you've shaded. That's an easy way to kind of check yourself. And then we can jump right to the calculator at this point. We've marked off 0, so we could say using technology, the command normal CDF, our lower bound is 0, our upper bound would be 1E99, right? It goes off the chart here. And then the mean is 4.5. The standard deviation that we use is 5. So I said it had to be over 50%, and the answer this gives us is 0.816. Okay, so that area is 0.816. What does that mean in context? So we'll look for you to give your answer in context, just like the conclude step. Summarize this answer in context. Well, that means there's about an 81.6% chance that that randomly selected male is going to be taller than the randomly selected female. All right, example 3 is about apples. It says, suppose that a certain variety of apples have weights that are approximately normally distributed with a mean of 9 ounces and a standard deviation of 1.5 ounces. If bags of apples are filled by randomly selecting 12 apples, what's the probability that the sum of the 12 apples is less than 100 ounces? Okay, so for starters, we don't know anything about 12 apples together yet. We'll get there. We do know the distribution for individual apples. So I'm going to use X again. If you want to use capital A, be my guest. I'm going to say X is the weight of a single randomly selected apple. So X is my random variable here. So X is approximately normally distributed. The mean is 9. The standard deviation is 1.5. And that just describes the distributions for individual apples. But we want to know about the sum of 12 apples. So I'm going to make a new random variable. Let's call it Y. You can call it whatever you want. And that's just going to be 12 different X's, right? 12 individual apples that are randomly selected. What X X is the weight of a single randomly selected apple. So now let's say what Y is. So we're going to let Y represent the total weight from the 12 randomly selected apples. And as far as a normal calculation goes, we need to confirm the shape, the center, and the spread. Well, Y should still be normally distributed because the 12 apples you're using come from a normal distribution. So Y is still following a normal distribution. And then the mean of Y, we add those 12 apples up, would just be the mean of X 12 times, right? So mean of X for the first one plus mean of X for the second one. So 12 times the mean of X, which is 12 times 9, or 108 ounces. And then the standard deviation for Y, well, we have to add up the standard deviation squared for each one of these 12 apples. So we'll start with the first one squared plus the second one squared. Then we get a little tired, we put dot, 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 all the way down to plus the last one squared. And then don't forget, we got to take the square root of all of those. So each one of those is 1.5 squared, and looks like there's a total of 12 of them. So square root of 12 times 1.5 squared gives us 5.196 ounces for the standard deviation of Y. Okay, so now we've got our Y distribution. It represents the sum of those 12 apples. We've got the mean, and we've got the standard deviation. Now let's answer the actual question. This should be a normal calculation because it says, what's the probability that those 12 apples will weigh less than 100 ounces? So what's the probability that Y is less than 100? Well, we'll make our curve. We know the mean, we know the standard deviation, so we can label it. And let's mark off about where we think 100 would be. And then we'll shade everything below that mark. And we can go back to our calculator. This is a normal CDF type of question. The lower bound, well, it goes off the curve here, so we'll keep the lower bound at negative 1E99. The upper bound is where we marked at 100, and then make sure you give it the right mean and standard deviation. And you should get a result from your calculator of about 0.062. So lastly, we just like to say, I know that's the area right here. All right, we illustrated that. What does this represent in context? Well, that means there's about a 6.2% chance that our 12 apples together, right, our 12 randomly selected apples, actually weigh less than 100 ounces. So I know we use a lot of stats notation. In fact, we use Y as our random variable, but our final answer in context here, anyone should be able to understand that. Whether or not they've had AP Stats, they can understand that there's a pretty slim chance that we get 12 randomly selected apples weighing less than 100 ounces. Okay, the last example here says, let B be the amount spent on books in the fall semester for a randomly selected full-time student at El Dorado Community College. Suppose that the mean of B is 153 and the standard deviation of B is 32. And we can only imagine those are in dollars, right? It says, recall from earlier that C is equal to the overall cost for tuition and fees for a randomly selected full-time student at El Dorado Community College. And the mean of C was 832.50. The standard deviation of C was 103. Find the mean and standard deviation of the cost of tuition, fees, and books, which would be C plus B, for a randomly selected full-time student at El Dorado Community College. What is the shape of the distribution? So as far as C and B together, why don't we just let that be T? So let T basically be the total cost, whether it's books or tuition. Let's add all that stuff up. That's going to be T, the total cost for a randomly selected student to attend this college. Then the average total cost, T, the mean of T, is actually pretty simple. You just do the mean of C plus the mean of B, and we're given both of those. So 832.50 plus 153 is $985.50. So that's the average total cost for a randomly selected kid at this college. Okay, but truthfully, that's as far as we can go for this example. In fact, we can't even calculate the standard deviation the way that we're used to. So the standard deviation of T in this case cannot be calculated. Why not? Actually, the standard deviation formula that we use says that the two things that we're combining have to be independent. And we know that the cost of books and the cost of tuition are not independent, right? So since the cost of tuition and fees, C, and the cost of books, B, are not independent, how can we be so sure of that? Well, students who take more units or more credit hours will typically have to buy more books. So those two things are actually very dependent. So keep that in mind. When we calculate the standard deviation, the two random variables that we're combining, whether we're adding them or subtracting them, have to be independent. And C and B here, right? Tuition and fees was C, and books, that was B. Those things are not independent. In fact, they're very dependent. Right? The more credit hours you have, right? The more of this you have, the more of this you have. That's just the way it goes. So our formula, right, if we were going to do standard deviation of t, if we were going to try to use this, that formula only works when we're combining two independent random variables. So that's why I definitely wanted to get to and feature this example as well. Keep that in mind, that our standard deviation formula requires that independence condition. And in this case, these things would not be independent random variables for any given student. And then as far as the shape of the distribution goes for t, we really can't comment because of the shapes of c and b. So we could say the shape of t is not normal since c and b aren't both normally distributed. So we can't say automatically that t is normally distributed. In fact, we can't really comment on its shape at all unless we find the shape of c and the shape of b and then look at the shape of t. But for sure we know that t is not normal, right? We can't take two non-normal things and expect to get a normal thing out of it, at least in this case. All right, so that's a really important example. Don't forget about the conditions for shape and spread, standard deviation. Also, don't forget when you're comparing two random variables, which one's bigger. Think about subtracting to get 0 on one side, and then what's the distribution for the difference of those two random variables. All right, that's enough for these notes. I'll see you in class.